Are you able to see the PDF that I'm sharing?
Yes.
Okay. I shared this copy of the PDF earlier on in the group so that everyone can have it in hard copy, because it is easier to read in hard copy than in soft copy. There is a lot of temptation in your phones, so you cannot focus when you are reading on the phone. And the beginning part of the PDF will give you an introduction about some mechanical properties of materials, which are basically the definition. So what you need to know about here around this are only the definitions. Then we shall begin at this at elasticity, at this section of it, which is the elasticity. That is what I want us to begin on. And if you are to see, I have highlighted some of the main points here, which will guide us through our discussions. So when you talk about elasticity, we are referring to that specific property of material that enables that material to return back to its original shape and size or volume when a deformation is removed. Normally, when you apply a force, a tensile force, something called tensile force to a material, meaning a force of tension, forces which is pulling apart a material in opposite direction. When you apply such a force to a material, what happens to a material is the different parts of the materials, which are actually the molecules, undergo what we call relative displacement. So the molecules are displaced from their mean positions, and due to that displacement, it causes the material to undergo through what we call extension. Okay? Yeah, so when the molecules leave their mean position, the length of the material increases, and that increase in length is what referred to as what? Extension. So all these happens because of what we call elastic what? Deformation. So a material that has undergone such a physical deformation is said to have undergone what? Elastic deformation. Yeah, so when you apply force on a material, the molecules of the material undergoes relative displacement from their mean position, and the material extends. After the extension, something happens. Okay? So an internal reaction, a reaction which is equal and opposite to the force you apply, will try to return back the dislodged what? Dislodged molecules to their position, to their original positions, and that is what brings back the material to its original size and shape after deformation. So a material that behaves in such a manner is called an elastic material. So an elastic material is one that returns to its original size and shape after what we call deformation. Are we together? Yes, so briefly, this is what we refer to as elastic deformation. So when you talk of elastic deformation, that is what we mean. And you should take that seriously. An example of a material that exhibits such a behavior of elasticity is a plastic material. Okay? And I can cite example of a rubber band. A rubber band, which is a rubber. So another example of materials that exhibit such a behavior is also a rubber. And a typical example that we know is a rubber band. You know, when you pull a rubber band side by side, when you pull a rubber band side by side, a rubber band elongates. And that elongation is what we refer to as extension. So when you pull it side by side, it elongates, and it increases in what we call length. So its length changes from the original length to a new length, which we can say L1. And then when you get a difference in this length, you get what we call what? Extension. So a material that behaves in such a manner is said to be elastic. Now when you release this force, the force which you had applied to the rubber band, when you release it, when you relieve the force, and if that force is within a particular limit, which we shall soon know what this limit is about, if that force is not exceeding this limit, then the material regains it what? Returns to its original size and shape. And then that material is said to be an elastic material. Yeah, so briefly, that is what is referred to as elastic material. There is a law that is going to guide us through our discussion of elasticity, and that law is developed by a gentleman who is called Hooks, Robert Hooks. He developed this law in relation to a force which is applied to an elastic material and the extension which that force causes. So Hooke's law states that the extension produced in a material is directly proportional to the load. This load can sometimes be referred to as a force. Okay, so don't be confused. You can even call it a force. So it is either called a load or a force. My pen is not doing well, but I believe I've written something. So Hooke's law says that the extension produced in a material is directly proportional to the force applied, provided this is supposed to be elastic. I made a mistake here. It's supposed to be elastic, provided the elastic limit is not what? Is not exceeded. So that limit, remember I told you that when that force is within a limit, and that limit here we have now found it to be called the elastic limit. When the force is within this limit, then that force, that the material returns to its original size and shape. But when the force is beyond this elastic limit, then the material now does not regain its original size and shape, and that type of deformation is no longer called elastic deformation. It's now going to be called what? Plastic deformation. So that is basically what this law talks about. So it's generally a relationship between an extension produced in a material and the force which causes that extension. So using math, if we remove this constant, this sign of proportionality, we have to replace it by a proportionality constant, which is represented in this PDF by this K. Yeah, so when you remove this and you swap it over, you have to begin with F. F will now be equal to KE, where K is the proportionality constant, which we are going to call it later as what? The spring constant. Yeah, sometimes it is also called the spring constant. This is for the spring, this K here. So we shall apply this law a lot, more especially on the numerical examples. Now, when you get an elastic material and you subject this material to series of loads, so that you monitor its extension, and then you plot a graph of extension against force, then this is how the graph is going to look. The graph is going to be straight from some point O up to a point L here. Then it is going to go through what we call a kink. There's going to be a kink, which is going to be this kind of a depression. Then again rise. Later on go through a very deep drop down, and then later on to vanish at N. Now we shall not talk about this graph in this section. We shall talk about it later. But I want you to carefully monitor this graph, how it is drawn, and then you should also learn to draw it the way it is drawn. So from O to A, the graph is straight. It it means that the extension produced is directly proportional to what? To the force applied. Then at L, the graph undergoes some sort of a kink. It means now the extension is no longer proportional to the force up to N. So at N, this is a point where now the string or this material here, which we have subjected to series of load, now breaks. So when you keep on increasing the load, there's going to be a point where the material will finally do what? Will break. So this point N is the point where the material will what? Will break. We shall talk about all these points in a later section. This is just to help us visualize what Robert Hooke was talking about when he said the last extension produced in an elastic material is directly proportional to the force applied. And that is a graph of extension against load. Now there are some other quantities that help us to describe a material, and some of these quantities are here. We have strain, stress, and Young's modulus. So these quantities will help us to analyze well the mechanical properties of material. We shall begin with the strain, which is represented by this small letter eta. This letter is called eta. This E looking kind of a letter is a Greek letter. So strain. When we talk of strain, strain is the fractional change in the deformation. Okay, is a fractional change in the deformed length of a material. So ideally it is the change in length, which is the extension out of the what? Out of the original length. So that is what strain is. So strain is a fractional change in the deformed length of a material, or it is a ratio of extension to the original length of the material. You can define it using any of these. In physics, when you don't know a definition but you know a formula, it is allowed for you to write the formula and then you define all the terms that are in the formula. It is allowed. That is also a definition. When you are asked to define strain and you have forgotten the definition, just why strain is equal to change in length out of original length of an elastic material. You have finished to define strain. The next one is stress. Stress is quite similar to another quantity. I don't know, do you see this? Stress is a ratio of tension force to the cross-sectional area of a material. Remember, it is a cross-sectional area, it is not surface area. So if this is the material we are talking about, if this is a piece of material we are talking about, then the area we are talking about is this area here. This area here. The cross-sectional area is what we are talking about. If you are to cut this material, then the area which you will see is what we refer to as the cross-sectional area. So a stress is the ratio of the force which is applied to a material to the cross-sectional area of that material. So if you guys, by now I know you have some physics, what quantity in physics is related to this tensile stress? Yes? What quantity is related to stress? If you were to compare by the formula. Can you relate it to something? Some other quantity in physics? A quantity that has its formula as force out of the area. What quantity is that? Pressure, right? Yeah, so stress is actually the pressure, which is, yes, it is actually the pressure which a material withstand due to a given amount of force. So stress is actually pressure inside a material. Now when we talk of tensile stress, we are referring to the stress due to tension or what? Tension force. So there are different types of stress which, for the sake of our syllabus, does not allow us to look at them. So we are only allowed to look at the tensile stress, which is due to tension force. So if the force is another form of force, maybe a compression force, then it will be a compressile stress. Are we together? Yeah, but if it is a tensional force, then we refer to that type of stress as a tensile stress. The same thing with strain. Tensile strain is also a strain which is due to force of tension, while compressive strain is a strain due to force of compression. So we shall be talking about only tensile strain and tensile stress. Yes. So one thing I've not talked about during strain is the unit. Strain has no SI unit. Why? Why do you think strain has no SI unit? Can someone guess? Because the extension is, if we were to use a standard unit, extension is increase in length, so therefore it is in meters, not so? And then the original length is also in meters. Finally, these two units cancels, and then we shall remain with no units. So the strain has no unit because it's a ratio of length. So both extension and then the original length are all lengths. So that's why the strain has no unit, and therefore it has no also dimension. When it comes to stress has unit, and the unit of stress is derived from the unit of force per unit area, which is Newton per meter what? Per meter square, and this is the unit. And if you have to see carefully, this is the same unit as what? The unit of pressure. Therefore, we can as well use pascals written capital P and small a, or pascals in small letters, as the unit of stress. So this now proves to us that stress is actually pressure. Are we together? All right. Then when it comes to another unit that another quantity that combines tensile stress and tensile strain, this quantity is called Young's modulus. Now, Young's modulus is the ratio of tensile stress to tensile what? Tensile strain. If you forget this word tensile and then you just say it is the ratio of stress to strain, you are wrong. That is going to be a different thing, none other than Young's modulus. So when you define Young's modulus, we look for this. We shall mark you wrong when you miss this word tensile. So it is a ratio of tensile stress to tensile strain. And if you are to use the other denotation we're using, we say it stress is force per unit area, and then strain is the extension out of original length. When you are to do math, you substitute these two. This is going to be what you will get. You will get force times length out of area times extension. I wish you could try this on your own and check if you will get this very formula here.
Question, sir.
So yes, go ahead and ask.
Is it ratio or ration?
It is ratio. This is a spelling error. It's a ratio. This is wrong, and that's why it is important we discuss these notes together with you, so that these simple mistakes we can omit it. It is a ratio, not ration. Yeah, you first check on this. Check on this formula. It comes out, and it must come out. Substitute it. Here you put force out of area. I'm using only one hand, that's why I can't do it quickly. One hand is recording this into a video. Then you put this extension out of original length. My original length, I have not used L0 because L0 is going to confuse us. I've used L. So we are going to use L throughout. But it's okay if you use L0. But if you decide to use L0, make sure you use it throughout. Yeah, so that is what we refer to as the Young's modulus of a material. There is a graph of stress against strain for different materials, and it's important we look at this graph one by one. We shall begin with the one of a ductile material. First of all, if you have read through the introductory part, you must have come across the definition of ductility of a material, which is a property of material which allow that material to easily be bent or into different shape. So if we subject a ductile material to different and increasing force, then this is how it is going to behave. The stress against strain of such a material is going to have this kind of a behavior you will see. I hope you're seeing it well. If you're not, then I can zoom it further. I have yes, I was able to zoom it to this size. Now when you look at this graph and then you compare it with the other one, let me check if I can open the other graph of extension again. Is the are you able to see this? Are you able to see the new graph I have projected? Yes? Can someone confirm? Hello? Are you guys able to see this new graph? I'm speaking to myself now. Yeah, when you compare these two graphs, the graph of stress against strain with the graph of extension against force that earlier on we looked at under Hooke's law, you see that the other graph is the exact inversion of this graph. Looks like they have tilted this graph. Look like we tilted it, we changed the axis. Instead of putting stress here, we put strain, and then here we put stress. Then to look exactly like the other graph of extension against force. So when you decide to draw a graph of force against extension, it is not going to be different from this graph we are looking at. It's going to be the same graph, okay? But when you draw the graph of extension against force, it is going to look like the other graph. It's going to be an inversion. It's an inverted graph, and you should take note of that. In exams, they can ask you to draw this one of extension against the force. So don't confuse it with the graph of force against extension. But if they ask to draw a graph of force against extension, then it is going to be this very graph, but now looking the other way around. And it is going to be the same graph as the graph of stress against strain. That is for a ductile material. Now when you look at this graph, point O is when you have not yet put any load to a material. You have not yet added any load to an elastic material. But when you begin to add the load to that ductile or an elastic material, the material is going to, at every time you add a small load you remove, the material is going to regain its original length. And then also the extension produced at every moment is going to be directly proportional to the force. Or the stress is going to be directly proportional to the strain in the material. So when you talk of stress, this is a measure of force. When you talk of strain, this is a measure of extension. Don't confuse the two. They are not so much different from the force against the extension. That's why they look the same, because stress is actually a measure of force, and then strain is a measure of extension. Yeah, so from point O up to point P, the graph is a straight line, implying that the stress applied is directly proportional to the resulting strain, or the extension produced is directly proportional to the force, and therefore Hooke's law is obeyed. So region OP is called a proportional region, and then point P is called proportional limit. Why? Because along this, the extension, the stress is directly proportional to strain. Now, when you move a little bit further to point E is a little bit, you see, from P to E is a little bit not a straight line. However, it is still somehow looking like a straight line, but is a little bit now bent. What does that imply? It implies, well, the material returns to its original shape and size, but the extension produced is no longer proportional to the what? To the force applied. And therefore, from P to E, Hooke's law is no longer what? Obeyed. However, the material still undergoes what we call elastic deformation. So point E, from O up to point E, the material still regains its original shape and size after the deformation is removed. And point E is referred to as the elastic limit. We shall check the definition down there. Now, when reached to point Y, from E to Y, something now occurs. The material does not now fully regains its original shape and size. Some extension now remains in the material, or some strain now remains in the material. So the material is said to have undergone what they call plastic deformation. And point Y is referred to as yielding point. So from E up to B, a material now undergoes what? Plastic deformation. Plastic deformation is that deformation which causes some extension to remain in the material. The material does not regain its original size, shape, or length after the deformation is removed. So from E up to B, a material is said to have undergone what we call plastic deformation. Now, point C, if you see point C is a maximum point along this curve, and therefore it is also called maximum stress, or it is also called, there's another name, which, let me check. It's another name which we call the point E. Sometimes they will ask you to define. It's also called breaking stress or tensile strength. So that is the maximum stress. This point E is the maximum stress that a material can withstand. That's why we call it maximum stress. It's the maximum stress a material can withstand. So beyond C, what is happening is the material now begins to thin up. The material reduces in size. There's going to be thinning, what we call thinning of a material. And then finally at B, it will break. So this is basically the behavior of a ductile material under stress and a strain graph. And then the explanation, I've given it thoroughly well in the notes. So you read the notes and then you'll get the explanations there. Now for a brittle material, unlike ductile material, brittle materials do not undergo elastic extension. Straight away goes through plastic deformation, small plastic deformation, and then breaks. Okay, so a brittle material, it does not go plastic deformation. It goes through a small elastic deformation and then straight away breaks. So if you are to see a graph of stress against a strain of a brittle material, which for example can be a chalk, a piece of glass, when you to apply a force of tension on a glass or on a chalk, the chalk does not increase in length, but immediately does this, it breaks. So it goes through a very small elastic extension, and then finally it breaks. Yeah, so I was interrupted by the baby. Sorry. So that's the behavior of stress against strain of a brittle material. A material that does not go through plastic deformation, goes through a very small elastic deformation and then immediately break. I want you to try it at home. If you can get a piece of charcoal, try to pull it apart, try to apply some tension on it, and you check if it's going to increase in length. What is going to happen is when you exceed the elastic limit of that charcoal, it will finally break, and these dotted lines are representing the breaking. Yeah, so there's not much about that. A brittle material undergo very limited elastic deformation from point O to point E. Okay, very limited elastic deformation from point O to point E, and immediately break if the stress is increased further. So the material does not undergo any plastic deformation. Should take note of that. Now when you are to bring the two graphs together, the graph of stress against strain for a ductile and a brittle material, sometimes they will ask you to draw on the same axis these two graphs. Then we shall have a graph of this nature that represents the two. For a brittle material, it is going to look like this, the first graph. Then for a ductile material, it's going to look like the other graph I explained before. Now for today, I want us to end here. I want to use only 30 minutes because if I record longer videos, you may not have enough data to view since the network has failed us. Tomorrow, as I told you, it is at 7 a.m. At 7 a.m. sharp, so make sure you wake up early. So at 7 a.m. But I'm thinking of pushing it to 8. So we shall have it at 8 because at 7, I think I'm not going to be available at 7. So let us have it at 8. So tomorrow at 8 a.m. sharp, we shall begin with this experimental determination of Young's modulus of a material. We shall look at this experiment to determine the Young's modulus of material into detail. I hope you watch this video carefully and follow it well so that you can understand with what you have in the notes. Thank you.